This lecture is meant to describe how to understand the torque by a magnetic field on a current-carrying loop of wire. So in a previous video and in your previous learning, you would have learned about how to understand the magnetic force on a current-carrying wire, and I'm going to add a word, segment. Right? And so what we imagined was there was some segment of wire. So here's some wire, right? And it has a length that is, say, L from, one end all the way to the other. It's some length L. And the current, let's imagine the current is flowing along this section of wire, has a current flow value I. So because the current is flowing towards the left, we can assign an L vector, which is simply, it has the length of the segment, and the direction of the L vector is in the same direction as the current flows along the length of that piece of wire, right? And if there's a background magnetic field, so some background magnetic field, then there's going to be a force on this segment, and it is by that magnetic field, and it is a vector. It's equal to I L. So I times L has to do with the current, right, and the wire segment, and then you vector cross product with the magnetic field that's in the background. But the thing is, we don't just have segments of wire that carry currents. Whoops. Right? That's not what normally we have in nature. What we have is current loops, right? Because circuits if you look at the word carefully, this word circuit, like electric circuit, right? It's sort of indicative of cycle or circle, right? So what we really have is current loops. So if you look at a basic circuit, right, you're going to have a little battery, and then you have a wire connecting the front and the back of the battery together. And in this orientation, you get a current, a conventional current that flows around this way, right? And the current's the same everywhere. And so if this current loop was in a background magnetic field, maybe I'll just draw some field lines. Right, so here is some background magnetic field. Then this circuit, the various parts of the circuit, right, the various segments that make up the total circuit are going to feel various forces. And so we could say that, like, this is a rectangular current loop, and what I'm going to do is I'm going to erase the battery, and I'm going to pretend that the battery isn't much to look at. I'm just going to say that there is a battery along this circuit that's providing the potential difference to drive the current through whatever resistance, right? So all those details are still there. I'm just going to not care about the battery and just concentrate on the loop. And I could have, the length of side 1 over here. I'm imagining this to be a rectangle. This is the length of side 2, and the length of side 3, and the length of side 4. And I could use this force law to calculate the force on side 1, the force on side 2, the force on side 3, and the force on side 4, right? And if I was, right, so these are going to be 4 individual forces on the 4 individual segments of this rectangle. And I could calculate what is the net force on the loop by adding together these 4 segments, where each segment or each force is calculated with the magnetic field near this section of wire, where that section of wire is carrying that current I. Right? So this is a pretty easily defined problem, and you can imagine going through the motions of solving for a net force. Yeah, so let's come up with a very particular situation. So I'm going to imagine taking this current loop, right, this black rectangle. So I'm going to imagine a rectangle, but I'm going to draw it from the side. So let's draw the rectangle oriented sort of diagonally. So here is, say, the near side, and then we get further over to the far side, and I'm trying to add some perspective, all right? So this is the near side and the far side. In the language up here, so it looks like number 1, right? The side number 1 could be the near side, and the side number 2 is the top, and the side number 3 is the far side, and the side number 4 is the lower side, like that. And I'm gonna consider, just for simplicity, let's consider a uniform background magnetic field. So a uniform background magnetic field is uniform in strength and direction. So I'm going to imagine that the magnetic field just points sideways everywhere. So I've got this image at this point, and the image is a little bit wonky. So what I'm going to do is, you can sort of see how I am converting this sort of starting picture that I have here into this sort of side perspective, but I'm going to clean it up a little bit more and really have a very nice sideways perspective drawing. So let me redraw the magnetic field. So let me draw a line to separate the pictures. Okay, so I'm going to redraw the magnetic field really carefully. I'm hoping that you can imagine that this is exactly sideways. Nice, parallel, straight magnetic field lines. And I'm going to imagine taking a perfectly from the side perspective. So all I'm going to draw is a single black line that looks like I'm only drawing side number 1. And I'm going to draw it at an angle like this. So that's side 1. And if I go and I look at side 1, that's the near side. Side 1 is this left side, and the current is heading upwards. So I'm going to remember that the current on side 1 is heading upwards. The current on side 3 is heading downwards. The current on side 2 is heading into the screen, and the current on side 4 is heading out of the screen. So I'm going to indicate that this way. I'm going to say that the current on side 1, which is the side you can see, is upwards. The current down here along side number 4 is out of the screen. And the current at the top along side number 2 is into the screen, right? So you use these X's and dots. So the dot means out of the screen, X means into the screen. It's just an aid in drawing in 3D. And I'm going to leave the opposite side, the third side, unlabeled because it's hidden. Yeah. So this is side 2, side 4, side 3 is hidden, and side 1 is being shown to you. So let's imagine using the force law, F equals I L cross B, to try to understand the forces on the various segments. So the force on side 1. So side 1 is interesting. You can see that it's this leaned over black line. The current is heading up, from the bottom right up to the upper left. But the B field is towards the right, right? And so if I wanted to understand the force acting on side 1, you can see that, first of all, it's got to do with the length of the segment. It's got to do with the sine of the angle between the segment and the magnetic field in the background. It's got to do with a few different issues. So it's going to look like, right? So let's actually just think about the magnitude of the force on side 1. It's equal to the current, right? So the current is just this positive number. And then L cross B. And if you do L cross B, what you're going to get is the length of side 1 times the magnetic field, right? So I'm going to take away the vector symbols and just talk about magnitudes. And then we have the sine of the angle between those directions. And the angle between the directions of L and B, L is up towards the left and B is towards the right. So the angle theta that we're talking about is actually that angle, right? So we could say that, that's the angle. And I've labeled it there. So the interesting thing, though, is the direction of the force on segment number 1 is given by the right-hand rule. And if you use the right-hand rule and you do this, what you're going to find is the direction of the force on line segment 1 is actually into the page. So the force on line segment 1 has this magnitude and this direction. So what's interesting to do is to think about what is going to be the magnitude of the force on segment 3. So segment 3 is this opposite segment, actually, and it's nice, actually. So I use the right-hand rule to get the force on segment number 1. So the force on segment number 1 by the magnetic field is actually in this direction. It points over towards the third side from the first side. And when you go and you calculate the magnitude of the force on the third side, it's going to be the same current. And if this is a rectangular loop, then the third side and the first side have the same length, but I'll just call it L3. And if the magnetic field is truly uniform, then the magnetic field over near the third segment is the same value as the magnetic field over by the first segment. So I'll just use the symbol B, right? And then if you take the sine of the angle, what's interesting is the angle is actually sort of a different sort of thing. So it's L cross B. So the angle between L and B is actually this angle, right? So it's going to be the other angle. So what's interesting, though, is it turns out that the sine of that other angle, it turns out that the sine of this angle and the sine of this angle have the same value, because what separates them, it's because of the sine wave. You can do a little research if you want. What's happening is, so can you see that this first angle that I labeled is bigger than 90 degrees? So the sine wave, goes like this. This is the sine of an angle as a function of the angle. And here is 90 degrees. And the angle theta is the same amount of angle beyond 90 as this second angle I'll call phi. So the angle theta is the same angle beyond 90 as the angle phi is smaller than 90. And this bump of the sine wave is symmetric about 90 degrees. It actually just gives the same value. Sine phi is the same as the sine of theta. So when you calculate the force, the magnitude of the force by the magnetic field on the third wire segment, you actually get that it has the same as the magnitude for the first segment. But what you're going to get that's different is when you use the right-hand rule, the force on the third segment actually points across over towards the first segment. Can you see that? What's going to happen is the force acting on segment 1 by the magnetic field is equal to, but opposite, the force on line segment 3 by our magnetic field. And so when we are calculating the net force, we're going to see that because the force on 1 and the force on 3 are opposite, the force on 1 and the force on 3, when you add them together in the net force, they are going to cancel, right? And that just makes sense. The wire on the sides is actually being squeezed. You can see these are squeezing forces. So we're depending on the wire to be rigid enough such that the magnetic squeeze, this magnetic tidal force, doesn't change the shape of our rectangular loop. So we'll just assume that. But what's interesting is when we go and we calculate the forces on the second and the fourth segments, you're going to also notice actually that those forces in the net force are going to cancel. That is, when you have a uniform magnetic field and you put a current loop in this uniform field, it will feel a net force equal to 0. This is going to turn out to be 0. So let's make sure that we understand why. So up here, right, we have a line segment of length L2, but L2 and L4, they're the same length, right, because we have this rectangular length. And if you use the right-hand rule on the upper current-carrying wire, so the current is into the page, and if you use the right-hand rule, the force on the upper segment is this way. Yeah, this is true. So this is the force on segment 2. And when you go and you calculate the force on segment 4, you get this arrow. And this arrow here, the force on 4, is in the opposite direction. Can you see the force on 2 is down and the force on 4 is up? But they have the same current, the same magnetic field strength, and the same length, so that the forces are going to be the same amount. And so what's going to happen is you're going to also discover that the force on 2 is equal but opposite the force on 4. And these are both forces by the magnetic field B. And what you conclude is that the net force on the loop by B is just 0. So what this means is my current loop is not going to accelerate in any sense linearly. So let's be careful. No linear acceleration. So linear means straight line, you know? Like if you considered, say, this loop being a piece of material, right? The center of mass of this loop is not going to accelerate. But what is interesting is there is twist. There's twist, right? And let me recall for you what the title of this little lecture is. If you look up at the top left-hand corner, this is the torque on a current loop, right? Torque on a current loop. And if you look at my diagram, that's exactly what's happening. There is a twist. And with twists, you can get angular acceleration. That is, the rotational motion is going to change, right? Not the linear motion, because the net force is 0, but there is an angular acceleration. So in a previous class, I think the symbol that's typically used for angular acceleration and torque is this Greek letter tau for torque, and for angular acceleration, there is alpha. And the torque is actually a vector. And the way you calculate the torque is you have to calculate this thing called R cross F. And this is, say, the torque by a force, some force. You could say it's the torque by force number 1 is you take the force 1 and you figure out where is that force acting. That's what R means. So the location where force 1 acts, cross product with the value of the force, right? And there's going to be a torque by 2 and a torque by 3 and a torque by 4. So there's going to be 4 torques, and there is a net torque, which is simply the vector sum of the individual torques, where I equals 1 up to 4. And it is a vector sum. So you add it up as vectors. So and then like this. So you can see, though, that in this problem, the interesting torque to calculate, because the force on 1 and the force on 3 are squeezing, they're not going to produce any torque, right? Or together. Together, they don't produce any torque. But what you do get, though, is because the force on 2 is down and the force on 4 is up, number 2 and number 4 are going to contribute to the torque. And they seem to naturally be torquing or twisting about a line that bisects sides 1 and 3. So I'm going to imagine, so let me put in blue a little dot. So the location where force number 2 acts is called R2. And the location where force number 4 acts is called R4. And they are the locations away from an axis. I'm going to choose this. I didn't have to choose this particular axis, but it tends to be one that makes a lot of sense, because if you think about it, the way this thing's going to rotate is about this midpoint. So I'm going to choose the midpoint as the location to calculate the torques, right? So let's clean up our drawing a little bit. So at this point, we have, here is the sideways view of our current loop, right? Wire number 2 is up here. Segment number 4 is down here. We have a force acting down at 2 and a force acting upwards at 4. And in blue, I'm marking the pivot point, and this is the location of where force number 2 acts, and this is the location of where force number 4 acts, right? And so let's go back into black. So there's force on 2, and this is the force on 4, right? So let's think about the torques. So the torque by force number 2 is R2 cross F on 2, right? And if you use the right-hand rule, what you find is this torque, one way you can think about it, can you see that that torque tends to want to rotate this thing counterclockwise, right? Counterclockwise. So by the right-hand rule, if you do this, you take your right hand and you orient your fingers along the first vector, right? You orient your fingers in the direction of R2, and then you rotate your hand until you can comfortably curl your right hand fingers into the direction from R2 into the force, the second vector. And that is going to cause your thumb to point out of the screen. So by the right-hand rule, the torque by force 2 at the position R2 is out. This is the direction of the torque, right? The torque by force 4 is R4 cross the force on segment 4. And by the right-hand rule, you can guess, actually, because it also tends to want to twist our thing in the same direction, it's actually a torque in the same direction. So these two torques, the net torque is just the torque because of force number 2 plus the torque because of force number 4. They're going to add in the same direction. They add out of the screen. So what about the magnitudes of each of the torques? So the magnitude of torque 2 is actually the same as the magnitude of torque 4. And this is easy to see if you think about it, because the distances are the same, the forces are the same, the angles are the same. So the magnitudes are going to be the same, right? Yeah, so because of this, yeah, you can imagine how the torque is going to add up like that. Yeah, so let's see. An interesting thing to point out is the following piece of detail. So let me add back or add the magnetic field direction. So remember, the magnetic field was towards the right everywhere, right? That was the magnetic field. And that's the magnetic field that the wire segments 2 and 4 are feeling. And so let's think for a second about something interesting. If I wanted to calculate the torque number 2, let's concentrate on torque number 2 for a second. So the torque number 2 is because of R2 and the force on segment 2. And that's going to include an angle. Let's call this angle alpha. So that's an angle called alpha, right? And when I calculate the torque number 2, if I want to know its magnitude, what I'll do is I need the magnitude of R2, right? So I need the magnitude of that vector, R2. I need the force, the magnitude of the force on segment 2, which is I L2B times the, and because of the fact that the wire segment number 2, can you see it's in and out of the page? So that's like you could say that's the Z direction, and the magnetic field points towards the right. You could say that's the X direction. So actually there's a 90-degree angle in calculating that force, the force on number 2. So when you go and you calculate that force, you're going to put in sine of 90, right? But the sine of 90 is 1, so I'm going to erase it. And that's all I've got right here, right? But let's think about R2 here. R2 is interesting. It's actually, it's half right? R2 here is half the length of segment number 1, right? Segment number 1 is this near side, right? Oops. Right here. You can see this segment number 1. So let's be really careful about the lengths. So when I calculate the force, I need the length of, this is the force on segment of wire number 2. So I put the length of wire number 2 there, but this is actually half the length of wire number 1. So when I go and I keep add in this thing, it's going to be the length of wire number 1 divided by 2, and then IL2B, like that. So that's the torque on 2, but I showed you why I expect that the torque on 4, oh, actually, I forgot a step, right? Because the torque is R cross F, I need an angle, right? I need a sine of another angle. And the angle that's interesting, actually, this one's pretty tough to see. Let me do something. I'm going to extend the direction of what's called the moment arm, right? Or I think that's called the moment arm. Anyways, I'm going to extend the direction of R2, right, with that black dotted line. So the direction of R2 is the black dotted line, but the direction of the force is this. So the angle that we're interested in is actually this big angle right here, right? So, but that story is, let's see, is that the same? Yeah, I think that's the same as the angle story that I told up here, where alpha is like the small angle, but it's the same amount of angle from the 90 degree as the other angle is on the other side. So this angle out here, if I called it beta, right, that big angle, that's the angle between the direction of R2, which is up to the left, and the direction of the force, which is downwards, right? So I've got that bigger than 90 degree angle. But I'm still going to end up with the sine of that angle, right? So that angle beta that I've indicated right here. So right now, this is pretty crazy, but you'll also get the same answer if you go through the process and try to figure out how to calculate the magnitude of the fourth torque. And the magnitude of the fourth torque is also going to be exactly this same expression. So it's L1 over 2, I times L2 times B times the sine of that angle beta. And then when you add together torque 2 plus torque 4 as vectors, the direction is again going to be out, right? That's because of the right-hand rule. But notice that when you add these two expressions together, that division by 2 goes away, and the net torque has a magnitude equal to, right, it's the magnitude of the vector sum, which is equal to L1 times L2 times B times I times the sine of the angle beta. Okay, so that angle beta, again, is, you can see it in this drawing. It's actually going to show up again on the other side when you calculate the torque by force number 4. That's that same angle beta. It's the same angle because the B field is uniform. So the direction of the B field lines are all parallel. They only point towards the right. And then this segment of wire is a straight line. So, that's sort of a classic geometry proof that these angles are the same. But yeah, they're the same value, beta. Okay, so yeah, so we have this expression. I want you to notice that this right here is the area of the current loop, right? I want you to notice that. It's also got this B value, and it's got the current I in it. But one big thing to notice is it's actually this net torque has a magnitude that's proportional to the area of the current loop. It's proportional to the area enclosed. So something about that area is important. And I'm going to show you in the next video how it's important. We're going to define a summarizing idea or quantity. And this summarizing quantity is going to be a vector. We're going to give it the symbol mu. So mu you might have seen because it tends to be used as the Greek prefix for micro, 10 to the minus 6. But that's not how we're going to use it in this particular situation. It's going to be a vector. It's called mu. And it's going to, so it has a direction that's important and it has a magnitude that's important. And it's called the magnetic dipole moment. And I'll describe this in the following video.